Hi everyone, welcome to the Maths for Design Optimization series, and on this very first part, the introduction. My name is Joy and I'm the founder and instructor from Optimize Academy. In this very first preview video, we're going to look at briefly what we're going to learn in this introductory course for the Maths for Design Optimization that is designed to give you an idea of what optimization is mathematically in engineering design. So the optimization we're looking at in this course is the optimization specifically targeting engineering design. There are a lot of other applications for optimization, for example, in operations research, where you're using optimization algorithms to design the optimal route for delivery, for example, or for your warehouse or any other logistics planning. Now, in this course, we're focusing specifically on engineering design. And at the peak of it was known as MDO, or Multidisciplinary Design Optimization, which is often regarded as the holy grail of complex systems design. In here, we emphasize the word complex, which characterizes systems that have a lot of layers or levels of abstraction and a lot of different disciplines within it as well. And some prime examples of complex systems include aircrafts, or satellites, or wind farms, or even submarines. So you can imagine the scale of this kind of system, not just in the size, but in the complexity of their design. Now, the conventional ways of designing these complex systems are pretty linear. Because it's complex, there are a lot of different teams within it to design this product. And most of the time, these teams often focus on their own domain or their own discipline and design just having their own discipline in mind. And once they've come up with a feasible design, all of these disciplinary teams then come together to assemble or integrate these different disciplines into the overall complex systems. However, as systems become more and more complex and the competition becomes more and more fierce, it's not enough to simply just create a feasible design. Your complex systems need to be better, if not the best, to stay competitive and to survive in today's landscape. And the way to achieve this also needs to be faster and more scalable as well. And this is where MDO comes in. A remarkable example of a large-scale MDO that consists over 25,000 design variables and over 2.2 million state parameters was able to achieve a staggering 80% improvement in performance, which is the data download rate of the product, which is a small satellite. So you can see doing MDO or not doing MDO in your complex system development can really make or break your system design and determine whether your product eventually wins the market share. And this is why engineering design optimization has become more and more indispensable in nowadays complex systems development. So through this series, I hope to provide you with the foundational knowledge on using maths for design optimization. And when we talk about maths or mathematical optimization, sometimes it may seem pretty unreachable to some of you because of all of the maths that we're going to go through. And it's also true that you can't do it effectively if you don't have a good grasp of the foundation. But what I want to say is that you don't actually need a maths degree to understand any of it. The way we teach mathematical optimization here is that we focus on building your intuition behind the theories or the principles that we're going to go through using a lot of interactive visualizations. So you can actually see for yourself why a formula is the way it is, or why an algorithm has such a strategy in mind. And we also provide a lot of coding exercises that are all based on real-world and practical engineering challenges, so you don't just understand the theory, but you also, more importantly, know how to implement all of these algorithms as well. So in this 5-part course, our goal is ultimately to design better systems and optimal systems as well. So in this very first part, the introduction, we're going to lay out the foundations of how we can define an optimization in mathematical terms, and also look at some of the workflow required in mathematical optimization study, and also try our hands on some simplest kind of optimization problems. Then after you have had a very brief taster of optimization, in the second part, we're going to look at doing some numerical analysis, which lays the foundation for an engineering design optimization, because it's about solving the models you developed to describe your complex systems. So in order to come up with an optimal design, you first need to know how to come up with a feasible one, right? So that's what part 2 is all about. Then on part 3, we're going to look at how we can compute derivatives, which are very essential if you want to use gradient-based methods, which is something we're going to learn in part 4. Gradient-based algorithms are often the more efficient kinds of algorithms, and they are very well suited for engineering problems, well-defined mathematical or physical governing equations or governing phenomenon behind them. That's why we want to take a particular look at this kind of algorithms. But also in part 5, the final part of this series, we're also going to take a different approach into optimization and look at the other family of optimization algorithms known as gradient-free algorithms. These kind of algorithms are also very valuable because they are particularly suitable under certain circumstances and situations as well. So all in all these 5-part courses aims to provide you with a very solid foundation and practical implementations as well that allows you to become fluent in implementing this kind of optimization algorithms for engineering design. So I hope you're excited. Now let's take a look at what we're going to learn in this particular introductory course. Now, in the first lesson, we're first going to look at how we can formulate a challenge or a problem mathematically into an optimization problem. We're going to also look at the process of doing an optimization study as well and some visualization techniques. And that brings me on to the first coding exercise, where we'll try to visualize some of the optimization problems so that we can get a feel for the problem that we're dealing with. We can then understand and build our intuition behind solving it and uncover any difficulties when we try to implement an algorithm. Then in the second lesson, we're going to look at the very standard or classic type of optimization problems called convex optimization. It also powers a lot of state-of-the-art algorithms, not just for convex problems, but for any other kinds of problems as well. So this kind of optimization study hopefully will give you a taster of how we can run an optimization in the full workflow. For our exercise, we're going to look at linear and quadratic programming, which is the simplest kind of convex problems that you can try on. And finally, with a more engineering and practical setting, we're going to look at the manufacturing production optimization for our coding quiz. So you can actually have a think for yourself, implementing the things that we've taught in the lessons in order to optimize the production plant or the strategies for a manufacturing plant, and have a taste of what optimization is typically used for in a real-world engineering setting. And that's it for the course overview and for this preview video. I hope you're interested, and I look forward to seeing you in the next video.